And basic tools, as I mentioned, are the laws of large number, CLT, and then the things that you derive from them. But after a while, like, well, people gathered sort of more data, like it's like 20 years ago, maybe 25 years ago, they started to encounter cases where you have like a gene expression array, like 10 to the 4 genes, maybe much more nowadays, but a sample of 50. Back then, it was like difficult to do, I guess, gene expression or like expensive. Maybe nowadays it's not, but you probably can go higher. If it's cheaper, then you do more genes, more samples. But let's say you have 50 samples of tissue and this many genes. So this is the sample size. This is the dimension. So clearly, asymptotic doesn't make sense. It's the other way around, basically. So like D is going to infinity, N is sort of fixed. That's the asymptotic that some people actually consider. You could, let's say, N be fixed, let D go to infinity. Or there's this other regime, which is very popular also, especially in random matrix theory, where you let N over D go to gamma. So N goes to infinity, D goes to infinity, the ratio goes to gamma. What we're going to focus in this course is like the non-asymptotic version. So D and N can be anything as long as we have a result, whether it makes sense or not. That's a different story, but you want to bounds that don't depend on the asymptotics. Usually you want to be able to say something in this case. The bound should be non-vacuous when D is much bigger than N. It's not hard to write down bounds that are not asymptotic, but it's hard to find bounds that are useful. Okay, so here's an example. Suppose I have this setting of 10 to the 4 genes and 50 samples. I want to do linear regression. Okay, so a linear regression model, you can think of it as, let's say, y equal x beta plus epsilon. This is a design matrix. So the if you're in the high dimensional setting, this is like n. D is like this, so it's a path matrix. So each row is a sample. So usually you write the rows, for example, as, let's say, xit. Okay. So we have yi, if I want to write it in the coordinates xit beta plus epsilon I. And then this is what? This is beta. This is d by 1. Okay, this is a big matrix vector. So I got the same dimension, like 10 to the 4. And then y is like n by 1. This is y, and this is noise. Okay. So we have I equal 1, 2. And so a linear model is just modeling the mean of this as some function beta of xi that's linear. Okay, so this is a linear, you can think of it as just another way of writing it. It's just a linear function of the input. So you can later change it to something nonlinear if you want, or but just a basic idea. So then this epsilon is the noise. So this epsilon is epsilon I is or IID, let's say. Or A0 sigma squared. Okay. That's the stochastic component. Usually for us, X is fixed. So you're dealing with a fixed design. And beta is the fixed parameter, fixed unknown parameter. So this is fixed. This is known. This is fixed unknown. Noise, of course, is random and unknown. And then Y is random and known. Okay. That's the basic set of a fixed design regression. Okay, so everyone happy with the regression setting? So we want to estimate beta, right? So imagine D was much smaller than N. We're not in this setting. How do you estimate what is a good estimate of beta? Yeah. Okay. X transpose X inverse X transpose Y. This is the sort of ordinary least squares OLS estimate, right? This X transpose X is d by d, because in this case X is like this, and usually you can assume that X is full rank X transpose invertible often, and this makes sense. So this is a solution of an optimization problem. It's the y minus x beta. So hopefully everyone knows. So this is minimizing this optimization problem, which is also the maximum likelihood estimate if we are dealing with the Gaussian case squared. And so it's the MLE. MLE in the Gaussian case. Has a lot of interesting properties. You can take the derivatives that are equal to 0, or do like argue from projection perspective. You get that the solution has to satisfy something like this. These are called normal equations, and then this is invertible. You invert it. Okay. It has optimality properties. Anyone knows, like, is it a good estimator? It's MLE, but yeah. Okay, best linear bias estimator. Blue, or best unbiased estimator period. If you're under the Gaussian, this is called the Gauss-Markov theorem. Right, because I believe Gauss actually proved it, version at least, sort of. Covariance of beta hat OLS is bigger, actually less than or equal to the covariance of, let's say, beta tilde, where this is any unbiased estimate. And this means this minus this is positive semi-definite. So if you look at the diagonals, it's just the variance of each component is bigger than the variance here. And even if you form linear combinations, this is the best linear unbiased estimator for any linear combination of betas that you want. So it has sort of optimality property as well. So it's a very good estimator, and it's used often. Like if you do regression, like in any software package, this is what they do. You have estimates of this as well. This turns out to be like sigma squared X transpose X inverse. You can have confidence intervals. You can have do tests, all sort of things. So the entire course is taught on this. Okay. So far, so good. So now what happens if I have not in this regime, but D much bigger than N? So what would happen if you're in the D much bigger than N? Can I compute the OLS estimate? Does this make sense? So the matrix is now like this. So X transpose X would be N by N, right? But I'm multiplying N by D, D by N, D is much bigger than, oh, sorry, this is D by, so it's like, it would be like this multiplied by that, and then I want to invert it. Would it be invertible? Yeah. Great, yeah. So this is D by N, N by D. So the rank of this is most N. It is much smaller, much smaller than D. So it's a very low rank matrix, so certainly not invertible. So this I can't even compute. How about this? Can I solve this? I can still take the derivative. I mean, I end up here. But is there anything wrong with this? Still low rank. Great. Yeah. So this will have many solutions. Okay. So there are least square solutions, but there are many of them. And you can also see it from here. If I add anything in the so the null space of the right is kernel of X is going to be non-trivial. So it's going to be a proper subspace. So this is not just 0, which is in the case. So it's like an entire subspace. And so if beta hat is a solution, beta hat plus U is also a solution. But let's say if, yeah, so U in the kernel. In fact, this has a more serious problem in the sense that this happens for the model itself. So I pick a beta, it generates a Y. I can pick a different beta by just adding something to the kernel, like from the kernel to beta. This generates the same, like giving the same distribution for Y. So statisticians call this like something, right? So yeah, so this model is going to be non-identifiable in beta. So beta is not an identifiable parameter because basically, if you imagine you're modeling the distribution of Y, I could have beta not equal beta not. That gives me p beta equal p beta. P beta not equal beta prime, but p beta is equal to p beta prime. So the distribution of data is the same for different parameters. This means that I can not identify the parameter. There's no way to estimate. This is the first check that you do if something like this happens, because eventually you're going to estimate the distribution of the data. There's nothing better than the p beta. And once I have p beta, I cannot invert the relation. So we have serious problems. And so then people look for solutions. There are a couple of solutions. I mean, some of them more classical than the others. But what are some of the solutions here? What can we do to sort of deal or mitigate this issue? At least give me some estimator, let's say. Although we have mentioned that this is not identifiable, let's try to estimate it and like see what happens. Okay, just produce some sort of. So non-identifiability is a very interesting issue. But let's say if I identify all these equivalent parameters with each other, can I recover one of them? Recover one beta up to a null space of, let's say, whatever, X. Okay, give me some sort of information about beta. What can we do? What should we do? You guys should know one, like at least one solution, two solutions maybe. Any solution would work as long as reasonable. So I have an optimization problem. Can I do something to this, let's say? Yeah. Add a constraint, yes. Okay, so we can add a constraint. Add a constraint. Or equivalently, like a penalty to the objective. Like by Lagrange multiplier idea, sort of equivalent. So we can restrict the parameter, or we can add a penalty on the parameter. So what should that? Yeah. Ridge regression. Okay. So what is ridge regression? L2. Yeah. So this argmin again, if I add the L2 norm squared, so everyone knows what the L2 norm is, right? So so LP norms are basically like summation I from 1 to n of f d beta I p to the 1 over p. Okay, this for any p bigger than or equal to 1 is a norm. L2 norm is just the usual Euclidean norm. So if I add the this here, this is called the ridge regression estimator. And this magically solves our problem to some extent because why? This is strictly, or yeah. Yeah, great. So this is another way of saying it is this is strictly convex. This is convex. This is strictly convex, or actually strongly convex. Adding it to it, the whole function is going to be strongly convex. There's going to be a unique minimum, and so you can take the derivative. Should we take the derivative or not? Do we want to take the derivative? Do you guys want to take the derivative or? Okay, we can take the derivative. X transpose y minus x beta. Let's not do it 1 over n. It's just going to rescale lambda. There's going to be 2 of this. Plus 2 lambda beta equals 0. And so you rearrange it, you get 2's cancel out, you get x transpose x beta. Sorry, y beta. Y something like that, okay? And then because of this lambda I, this is going to regularize. This is called the regularization. Okay? This regularizes it, and it's a very old idea. So it's called Tikhonov regularization in inverse problems. And then you invert it. So this is always invertible because the eigenvalues, it has a lot of 0 eigenvalues, but you shift it by lambda, all the eigenvalues are going to be lambda or above. And if lambda is strictly positive, this is going to give me the regression estimator, beta hat RR, which is x plus lambda I inverse y. Okay. So now I have an estimator uniquely defined for every lambda. And believe it or not, this is a good estimator. Okay. Simple, but good. In a particular way, it's a good estimator. But the question is that in what way it is a good estimator? So can I hope that this recovers the true beta, let's say, in some sense as like sample size maybe grows or? No, okay. It's a good point. So the answer is no, yes. So let's say if we are in this regime that n is much smaller than d, let's say they grow, both grow. So n grows, but d also grows like the same rate or bigger. There's no hope that that can recover the beta consistently. And now I'll assign it as a homework problem, but you can show there is a version of it which is so let me mention that. So there is one problem with this. By adding this, we lost unbiasedness. So if you look at this, this is going to be always biased for any lambda. That's fine. I mean, you realize in high dimensions, it's fine to regularize. It's fine to be not unbiased as long as the bias sort of goes away. But let's say there is like a special case of this, which is if I let lambda go to 0. So the limit of this as lambda goes to 0 gives me something. Anyone knows? It should be x transpose. So you can think of like 1 over lambda here. If I factor out lambda, argmin is going to be the same. So I factor 1 lambda. As I let lambda go to 0, this gets very big. Okay, and I'm going to start trying to solve like betas that satisfy this strictly. Like when lambda goes to 0, my beta is going to be solving this equation exactly. but I'm also minimizing this. So among the solutions of this linear equation, I'm going to minimize, I find the ones that minimize the beta. Okay, so the limit as lambda goes to infinity, or lambda goes to 0, would be, if I'm not wrong, would be, just correct me if I'm wrong, but it will be the minimum norm solution. So you solve this. That's like the limit. Let's say 0 plus. That's like if you go to 0. Something like that. So this doesn't have any beta in it. And it's a classical way of dealing with overdetermined system equations. So if there was no noise, I would try to solve it exactly. And usually you'd work with, if you do it in like numerical software, usually you do minimum norm solution. So you can work with this. The solution of this would be like, would be exactly look like that, but you would replace it with the pseudo inverse. So if you treat that inverse as pseudo inverse, this is going to always exist, and that's sort of that you can work with this and show that I'm going to call it pseudo inverse. Beta hat minimum norm or pseudo inverse, say min norm. Minus beta. Let's say this was beta star. Expectation would be of the order sigma squared d over n, something like that. But at least you can show that up to constant, this is going to be bigger than sigma squared d over n. It still remains much bigger than n. There's no hope that this goes to 0. You can try to do it. We'll see whether we can assign it as homework problem. But the main idea is that there's going to be the noise level, there's going to be the dimension, and there's going to be n. So as long as usually you'd see these things like d over n, as long as dimension over n is big, there's no hope. Okay, although you have an estimator, you can't estimate this. If you want to estimate x beta hat, there is hope. This is the prediction problem. But we're not going to talk about this. So if I want to estimate the mean, but if you want to estimate the parameter, there's no way I can estimate the parameter. Intuitively, it should be clear because if this is a dense vector, they're d parameters, and there's just not enough data to estimate all the parameters. Okay, so from n observations, even if they're perfectly uncorrelated, let's say a very good design matrix would be just 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. I'll pick like d of like n out of this perfectly, and the rest are not observed. And if I get a general linear combination, I'm mixing things up, which is going to be harder. So I'll leave this like in a footnote. Prediction problems are different a little bit. Yeah. Can you say? Okay, beta star is like the true beta. So what I'm trying to say is there is a beta star that generates this beta. Yes, so beta hat is this. Beta hat min norm. Yeah. I'm not talking about this one, but this one is, yes, no problem. So the point is that it's not possible to do it with this classical ridge regression. So what is another solution? How should we solve this? Do you know what people did like classically to deal with this? So what they did is to put more assumptions in beta, basically. Without assumptions, we can't do anything. So assume something about the beta. Imagine that this version assumes that beta star was actually the minimum norm solution of this, but that's not good enough. We need another assumption here. No one. The norm is equal to, sorry? That's not going to help. Yeah. So if you assume the norm is equal to 1, it's just one constraint. And generally speaking, I can rescale the design and rescale this. That's not going to get rid of the difficulty of the problem. Yeah.
You assume a bunch of them are 0.
Yes. Okay. That's exactly what people assume. So you're going to assume, like in reality, let's say this is controversial, but you hope that like a few of these, let's say, genes are driving whatever disease that you're trying to model. So this is like blood pressure, sort of just a few of these 10 to the 4 are yeah. So you'd imagine that maybe a lot of them are 0, a bunch of them are non-zeros, but like maybe 10 of them are non-zeros out of 10 to the 4. But the difficulty is that if I knew the locations, then I would just set everything equal to 0 elsewhere. And then my problem reduces to a 50 by 10 dimensional regression. We're back in the classical setting. The difficulty is that people are willing to assume things are 0, but they're not willing to assume that you know where the zeros are. Okay, so or the non-zeros are. And that's where the sparsity idea comes in. So we're going to assume, or they assume, like beta is, so sparsity assumption. So you could say beta. If 0 is less than s, if 0 not the proper norm, but this counts like how many entries are non-zero. So it's the cardinality of the support of data. And so called L0, that's the limit of the LP norms. And this is, we're going to assume it's less than S, let's say. This is called the hard sparsity assumption. At most, S of them are non-zero. There is still a complexity in the problem in that there are D choose S possible ways of choosing these. Okay, so this is going to be like of the order of, let's say, D over S to ds. Okay, or if you want, like d over S to ds. And if S is also like growing, I think like exponential in S, polynomial in like, if S is fixed, it will be polynomial and it's pretty big. And if S is also growing, maybe S like grows with everything else, but not fast, but this would be exponential in S. So there is this problem that you have to search over this big space of all possible subsets. I can do like, assume that I have a particular subset that is like a simple solution. Let me ask you, what is a simple solution? So I have this assumption. How do you solve the problem? Yeah. The largest what? I don't have the betas. Them first. The simple solution is a search for beta. So you have this many subsets, you just go and fit all these possible regressions. So all possible subsets that are non-zero. So I'm going to solve basically, so beta hat, let's say, I don't know what should we call it, L0 if you want. This is like argmin y minus x beta squared, beta 0 less than or equal to s. Like condition, this would be equivalent to solving something like that. Argmin over, first I choose the subset that is non-zero, S, such that cardinality, so S subset D, this is all this notation is 1 to up to D. So a subset of all the coordinates such that the size of the subset is, I can just assume is equal to S because smaller subsets are contained. This S and then argmin, and then another min, okay, min over, yeah, bad notation, but let's say beta S. S beta S. So here, X sub S is matrix X restricted to the subset S. So if this is the subset S, I'm just going to pick these columns. Okay, so that would be XS. So just pick the columns of X that are on subset S, and beta S would be, it's just a dummy variable. We can imagine that it's just beta restricted to a subset S. So this is going to be n by S. This is S by 1. You can call it some gamma if you want. But I'm just going to fix the subset, solve this problem, and then vary the S, and find the S that minimizes, like among all the, let's say, possible subsets, what minimizes this. Okay. So each individual one is a reason. If S is much smaller than D, let's say S is less than N, let's say S is like 3, N is 50, each one is a well-defined, regular regression. But I'm solving many of them at the same time, so I'm going to still pay a price. Okay, there's going to be errors in this, and then errors sort of add up in a sense of like, once you do a lot of random things, so you're solving optimization problems that involve the noise, and these noise are dependent. Okay, and so I'm going to pay a price. It's not going to be as clean as just solving one of them. I'm solving multiple of them and finding the one that minimizes it. But this is a solution. Okay, this would work in very general settings, as long as, let's say, smaller than n. If D is much bigger than n, but S is much smaller, then this would be a good estimator. So we close to. That's you can also think of a regularized version where I add like a penalty here with a 0 norm. It would be similar. Okay, instead of this, I could add it as a penalty. But the main idea is that I'm just gonna search. With the L0, I have to search basically. This is not a smooth penalty, so I can't take derivative or something like that. But what is wrong with this? Statistically, this is a good estimator. There's something else going on that's not desirable. So imagine I have 10 to the 4, like, and then S is like 10. Yeah, so the search problem is problematic because B choose S is like 10 to the 4. This is pretty big. This is like of the order. It's not 10 to the 5, but let's say 10 to the 4 divided by 10 to the 4 is this. Okay, so is it 10 to the 4 or 10 to the 5? Should be big. Should be much bigger. Oh, actually, sorry. 10 to the 4 divided by 10 to the 10. Okay, not to the. This is like going to be 10 to the 4 was very realistic. This would be like 10 to the 3 to the 10 would be like 10 to the 30. Roughly this many. Which is you can imagine if like this was 100, I'd get a very rough estimate, but with 10 to the 2, 10 to the 200. That is not doable anymore, okay, at all. Something like that. Just do the calculation for yourself, but it gets very like exponentially big. Um, so what should we do now? We have a good, like, haven't shown it, but you can, by the end of the course, you should be able to like analyze this and show that this is estimate, like consistent under some mild, not mild, but reasonable assumptions. Annotation is not good, but how people understand. So this is just imagine solving this and think about how to solve this, and you arrive at this solution. So what should we do? What did people do next? Yeah.
You could choose like random subsets to switch over.
That's a good approach. Have people done this? I don't know. But you can try to analyze it, see, pick random subsets. But the question is how many you have to pick, right? So if I could reduce this number much to a much smaller subset by doing random selection, then that would work. I don't have a recollection that people have done this. We'll do some sort of a random approach, and it works in a lot of cases. But whether in this case it's going to achieve, the thing is that your random subset should integrate with some good probability. You can try to calculate whether you're going to pick the right subset. So if I might have to like increase to this order. I don't know. Right? It's a good thought. So like solution random subsets. Maybe you can think about it. But what else can you imagine? So it's interesting. So you haven't heard about the actual like the solution that people. This course is going to be exciting for you then. It's just there is a very neat solution to this. Have you heard about Lasso? These courses? No? So what is you have heard? What is the Lasso? Okay, yeah. So that's the solution. So people got like very excited when they realized you could just replace this. I could put it as a penalty here. I could relax it not to L2 but to L1. Okay, so if I replace this with L1 or and this is called the Lasso, and this has a lot of desirable properties. First, it's a convex problem, and it's actually reducible to a linear program, and so you can actually solve it efficiently and exactly. And the second is that this is different than the L2, and it tends to produce zeros, a lot of zeros. So the optimal solution would have a lot of zeros. And this will come clear if you write down the optimality conditions. In order to satisfy this, a very simple thing to note is that like this is the sum of of a bunch of absolute values of the entries, and absolute values look like this. There's a kink at 0. Okay, because of this kink, when you add it to take a quadratic and try to minimize, there are cases where 0 is like the solution, the optimal solution. If you 1 in 200b, like the Bernoulli example, like last quarter, just imagine try solve like something like this, x minus, like y minus beta squared plus lambda, revariant, argument over this is not differentiable, so equal to 0, but imagine this over beta, and you can see for certain values, the solution would be exactly 0. And you can use convex optimization or convex analysis. You can show this, and the subdifferential would be a set. So at this point, it's not differentiable, but and there's like a whole set of subdifferentials. In any case, we can talk about this later. But if you've taken up like a convex optimization course, you get a very good feeling of why this will produce a lot of zeros at the optimal value. I think because maybe those zeros are actually true. Maybe those zeros are actually what we're after. And this sort of got like out of hand. People started like analyzing it very vigorously, and then they managed to show. So under some conditions, there's the solution of this is going to be like it behaves something like roughly like S log D over N times sigma squared. Okay, instead of, so this part is very similar to sigma squared D over N, but now we have S here, and then there's this log D, so the dependence on the dimension, the ambient dimension is going to be D. And this is the price, this is the extra price that you pay for the search of the unknown subset. So it's almost as good as if you knew the subset. If you knew the actual subset, you could show you can do better than this. So let's say if there is S, non-zero entries, and you focus on those exactly, the best that you can do is like sigma squared S over N. That's the scale of the error that you get. And then people showed that by choosing the proper regularizer here, so lambda should be a certain way, and some mild conditions, then you can achieve something like that. With more conditions, you can actually recover the actual support of this. So the non-zero pattern of this would match the non-zero pattern of this. That's called the support recovery or model selection consistency. It's much harder, much more restrictive assumptions, but this is already good. This has got what people got really excited about. Okay, this is saying that this could be exponential, like 10 to the 4. Only the log matters as long as S is much smaller than it. So I really don't pay the price that you'd imagine you'd pay by trying to estimate 10 to the 4 parameters. And this is roughly like the log of the size here. So this is roughly this log. Okay, that's where it comes from. So that's the whole sort of, I would say that's like history / introduction. Okay, so we want to get to some sort of a result like this. And then from this, people try to extend this to other problems. So what if I want to estimate a matrix? The equivalent of sparsity for matrices is being low rank, let's say, or some sort of a low rank. And then they try to come up with other assumptions. There's another set of assumptions that are, there are other assumptions. Okay, so I can probably ask you guys, but let me stop and ask whether it's clear. Is there any questions? So we want to build tools to be able to maybe say something like this about the Lasso. Okay, can we like prove a result like this? And once you have the tools, once you understand how to prove this, you can like do other stuff. Okay, do more. You can change the laws, for example, to classification. You can analyze logistic regression, like general exponential families. With a bit of work, you could do like matrix completion, low rank recovery, other sort of cool stuff, let's say. Sounds good? How much time do we have? It's like 2 to, we got 15 minutes. Right, okay. So let me mention some of the other possible assumptions. Another set of assumptions is that this is like block constant. So suppose you have, these are like, the indices are time. Okay, and then this is just constant up to a certain point and then jumps. Okay, this is natural, let's say, in time series analysis. So you have a phenomenon, the mean is like constant, or like the effects are constant up to this point and then jump to something else and jump to. So that's the block constant estimate. And sort of roughly the derivative of this is going to be sparse, or the difference sequence would be a sparse. So block sort of constant structures can be done by something like this, but instead of applying it to beta, we apply it to the difference sequence. So beta I minus. So instead of this penalty, I would do something like beta I minus 1. That's called the fused Lasso penalty. Okay, so because this tends to produce a lot of zeros inside here, I would when things are 0, it means that beta I is equal to beta I minus 1. So it's going to be 0 in a lot of points. So beta i's are constant and then jumps to something else. So you could do this with fused Lasso. There's another version which is group Lasso. So I might imagine that there are groups that I know, and I want these groups to be 0 entirely. So let's say these are genes associated with a certain trait. I know that if one of them is not effective, the other ones are not going to be effective. So I want this particular part to be either 0, all of them, or not. Then you could do the group Lasso penalty, which is something like beta subset G, let's say K. This is the subset of the entries that are grouped in group K. Okay, and then you put an L2 penalty. Again, this is like the L1 on this. So this is going to produce a lot of zeros here, and the entire sort of matrix is going to be 0. There is another classical approach where you impose sort of a smoothness, not on beta, but let's say on the function itself. So you can imagine that this is a function here. Loss. So it's a non-parametric regression. This is a case where f is linear. Linear f is very smooth. But if I really non-parametric regression, I could have a general function here. Again, I run into the issue that the parameter space is very big. So usually infinite dimensional, I have sample size n. How am I supposed to estimate a function which is infinite dimensional? And then you impose, this is very classical, much more, much earlier than stuff. You impose smoothness. So suppose the derivative is not varying as much. Then you would solve things like, I'm gonna find the function that minimizes this over the class of functions plus a penalty, let's say, which is like the integral of the derivative of this squared. So this is a roughness penalty. So if the derivative varies a lot, this is going to be big. So I'm going to penalize the derivative. These could, in some cases, be reduced to finite dimensional problems using the kernel methods, the kernel trick. And then the corresponding coefficient. So this function, so you can reduce it to a finite dimensional problem, and the smoothness penalty would impose a certain structure on the betas. I mean, maybe we get to it, but it's discussed in the book. So you would get an ellipsoid condition. So this is in an ellipsoid. So it's just the norm condition that you mentioned, but it's a particular norm, not the L2 norm, but it's saying that in certain directions, there's not much, but in certain directions, there is a lot. So if you impose a condition like that, I should like take back that the norm would work, but it should be a norm assumption on beta. If the norm sort of imposes the condition that a lot of the entries are not big, okay, then you would do good. Okay, sounds good. Okay, I think this is enough of an introduction. So I'm going to leave this setting. So this is the background that we're going to work towards. But for the next few lectures, I'm going to focus on concentration inequalities to be able to like get the tools to attack this problem. Okay, and these basic tools, the concentration inequalities, if you haven't seen them, they're very useful in their own right. So even if you don't want to understand this, you can later on hopefully use these in your other, like, analyze your other problems. Okay, so how many people have seen concentration inequalities? Okay, a bunch of you. So most of you have probably seen it, but maybe not under the name of concentration inequality. So these are the things that provide inequalities for these type of probabilities. So if I have a random variable, I have an expectation for that random variable. What is the probability that this deviation is bigger than some t? Okay, and you want it to be like less than something small, let's say. So you want to say the random variable is close to its mean. And one way is to say that the probability that deviates from the mean is small. The classical example, which is like the building block, is the Markov inequality. Okay, so if you have a random variable which is non-negative, the probability that x is bigger than t is less than the expectation of x divided by t. And then from this, basically, you can build everything else. This doesn't look like this, but if you imagine that this is a non-negative variable, if I apply it with x being this deviation, then I get a concentration inequality for x. Because this is going to be the building block, anyone remembers how to prove this? Just to be complete. How do you prove the Markov inequality? For the sake of completeness. All right, okay, so let's do this. And what? What is the definition of expectation? You mean the integral, things like that? I want to avoid writing the integral, okay? Is there like a cleaner way of doing it? I'm going to write it as the expectation. Can I write the probability as an expectation? Indicator variable, yes. Okay, great. So probability is the expectation of the indicator. Then I can move the t inside, right? Because this is linear. The inequality is really this. Okay, this gives you an idea of what you actually need. So if I can show that maybe this holds, if this holds, then I can take the expectation of both sides. Expectation is monotone, I get this and I get that. Okay, so this gives me that and this gives me this. It's very simple. Is this true? This is basically, you can think of it as just a deterministic equation, holds for any x in t. So if I want to plot, this is the graph of this function. Okay, f of x is equal to x. It's like f of x equal to x. This is what? This is a graph of another function. It's 0 if x is bigger than t, t is positive. 0 where x is bigger than, sorry, it's 1 where x is bigger than t, right? And it's going to be exactly equal to t. So if this is t, this is t, this is going to be like this here, and then like that. Right, so it jumps. So that's the graph of, let's say, g of x, t1, x bigger than or equal to t. You can see that this is less than or equal to this if we are in the positive region, right? So because we're assuming this holds for any x bigger than or equal to 0 and t bigger than or equal to 0. The bad part is here, but we're in this regime. So this is strictly less than this. This is a pointwise inequality. Apply it to the random x, take the expectation. Okay. It's like a clean way of doing it without any integrals, and you can see it holds like generally. It doesn't have to be random variable, doesn't have to be continuous, or like densities exist, things like that. So if you have this, then I can apply it to So apply it with x replaced with x minus mu squared, right? That's a non-negative random variable. So apply the Markov inequality to this. This has to be bigger than or equal to t is less than or equal to the expectation of x minus mu squared divided by t. Right, I'm going to put t squared here. I can do anything I want here for t as long as it's not negative. And then I take the absolute values. Let's say t is not negative. This is like, sorry, take the square root. This would be it's bigger than or equal to t. Less than this is the variance of x t squared. Okay, so this is the Markov inequality, right? And I can repeat this by applying it to the power k here. I get the k central moment divided by t to the k. So why should we like let's say do Chebyshev? So you can see that this is the tail is going down like 1 over t here, 1 over t squared here, 1 over t to the k. Goes down faster. So it seems like more k is better. Okay. So why should I say, why do people work with Chebyshev where they can like do the third or fourth or fifth moments to get better tails? Variance is easier. Yeah, okay, so variance is easier. That's a good like practical concern. That's true, but there's a more fundamental issue. Sometimes you can just do this, but can't do this. Yeah. Yeah, so in order to be able to do this, you have to assume that the kth moment exists. Okay, a lot of variables don't have, like, let's say Cauchy random variable doesn't even have this, right? The expectation doesn't exist, this is like infinite. So this doesn't hold for Cauchy. But let's say for a random variable whose second moments are finite, I can do this because this side is finite. So this bound holds even if this is infinite, but this side would be infinite. It's not useful. And so the thing is that as long as your like moments up to k exist, then you can do this bound and you have this tail. And this is the general idea. The random variables that have the higher moments are finite, the tails are more controlled. Okay, like Cauchy has a very heavy tail, so it's not like dominated by something like this. But let's say a random variable whose second moment is finite, the tails are going to be at least going like 1 over t squared. And this is going to be a sharp inequality in the sense that there is going to be a random variable whose moments are like second moment is finite, and just the tail is exactly like that. It can't go faster. Okay, if you just assume something like this, you can't improve this inequality. It's not like improvable. The only way that you can improve this is by assuming that the more moments exist. So this is holding under like less assumptions basically. And if all the moments exist, what you can do is that you can take the infimum here over k. Okay, write this for all k, and then minimize over k. Whenever you have a bound that has a parameter, that would be the best bound that you can get. And if you believe the HDS book, that would be even better than the exponential bounds that we will come up with. So that would, the best like moment bound would be better. But anyway, so we're out of time. Next time, I'm gonna hopefully come out, like come and talk a little bit about the relation to the CLT and then derive some of these so-called sub-Gaussian bounds and then sub-exponential bounds. These are building blocks, and then we build from there. Okay, questions, comments? Okay, so let's stop here. Thank you, guys. See you on Thursday.